Hello everyone. In this video we are going to see about the subject control system unit 3 frequency response and system analysis. In that the topic is Bode plot. Objectives. At end of this video we gain a knowledge of various methods for analyzing the frequency response and the stability of the systems. Bode plot. Generally, Bode plot is the frequency response plot that contains two graphs. One is magnitude plot and the other one is phase plot. Bode plot can be drawn for both the open loop system as well as the closed loop systems. But also it is generally drawn for the open loop system because it conveniently determines the stability and other related parameters also. Bode plot. Bode plot is used to determine the stability of the systems. And then the standard representation of the Bode plot for the open loop system is given by 20 log of magnitude of g of j omega. So these are all about the introduction of the Bode plot. And next we are going to see about the procedure to draw the Bode plot. The first step is, before we are going to see about the procedure how to draw the Bode plot, let's discuss the main conclusions obtained from the topic are the constant gain k, the derivative factor, the integral factor in the Bode plot. These are all contributes the gain at all frequencies. If we have the higher order in the sense means two or more factors in the transfer function means this contribute gain only when the frequency is greater than the corner frequency only. And then one more conclusions from the Bode plot is, in case of quadratic factor the natural frequency is assumed as the corner frequencies. Now let's discuss the steps that will help us to draw the Bode plots. The first step is, first we have to convert the given transfer function into the time constant form. How means it helps us to easily find the corner frequency by using the first step, that is we have to convert this transfer function into the time constant form. And the second step, we have to arrange the corner frequencies in the arranging order. That means in the increasing order. And after the arrangements of the corner frequency, we have to select the frequency which one is having the lower value compared to the corner frequencies. After this comparison only, we have to calculate the value of the terms at the selected frequencies. After the frequency calculations, we have to find the gain in decibels one by one at every corner frequencies. How we have to find the gain means, we have one formula to find the gain is, that is the gain at omega y equal to slope from omega x to omega y into log omega y divided by omega x plus gain at omega x. This is the formula to find the gain in decibels for every corner frequency range. After the gain calculations, we have to perform this step number 4 again at the different frequencies, in the sense higher frequencies, that is which is greater than the highest corner frequencies. After we have to find the different corner frequencies, we have to mark the points in the semi-log graph, and after the marks will be pointed on the semi-log graph, we have to join the points that will be in the form of straight lines. After we have to plot in the semi-log graph, we get the complete Bode plot. But the complete Bode plot is assumed as only a approximated plot. The exact plot requires the exact calculations at every corner frequencies is our original exact plot of the Bode plot. So these are the steps we have to follow to draw the Bode plots. Next we are going to see about one example. Here the given question is, sketch the Bode plot of the following transfer function g of s equal to k into s square divided by 1 plus 0.2s into 1 plus 0.02s. Also determine the system gain and the gain crossover frequency omega gc to be 5 radians per second. This is our questions. First, how we approach these questions means, first we have to write the given transfer functions. The given transfer function is g of s equal to k into s square divided by 1 plus 0.2s into 1 plus 0.02s. The first step we have to find the corner frequencies. How we find the corner frequency means, first we have to substitute wherever we have s in the transfer function, just we have to substitute j omega. So in the given transfer functions, g of j omega equal to the k as it is k, and then s square in the terms j square omega square divided by 1 plus 0.2 j omega into 1 plus 0.02 j omega. So in the denominator we have two poles. So we have two corner frequencies that can be represented as T1 and T2. That corner frequency where means at a point 2 and 0.02. Then the first corner frequency is 1 divided by 0.2 can be written as 5 radians per second, and 1 divided by 0.02 can be written as 50 radians per second. So this is our procedures to find the corner frequencies. After we have to find the corner frequency, we have to prepare the table for different corner frequencies. So in the given transfer functions, we have three independent factors. The first one is j square omega square, and in the denominator we have 1 plus 0.2 j omega and then 1 plus 0.02 j omega. We have to prepare for this three factors. So in the tabular column we have 4 columns. The first one is a representation of the term in the transfer function, and the second one is the equivalent corner frequencies, and then slope in decibels and in change in slope. It is also represented in terms of dB. The first term in our transfer function is j square omega square. So we didn't have any corner frequencies for this j square omega square terms. Just we have the slope at 40 dB. And in the denominator we have 1 divided by 1 plus 0.2 j omega. So for this term we have the corner frequency at 5 radians per second, and we have the slope at minus 20 dB, and the change in slope is given as 40 minus 20 equal to 20 dB. And the denominator we have one more term, that is 1 divided by 1 plus 0.02 j omega. For this we have the corner frequency of 50 radian per second, and then the corresponding slope for this term is minus 20 dB. Then after that we have to find the change in slope. How means we have to already we have 20 minus we get minus 20, at last we get 0 dB. This is the representations of the independent factors that we will have in the given transfer function. After that we have to find a frequency that is lower than the first corner frequencies, as well as we have to find the frequency that is higher than the second corner frequency. Already we have know the standard representations of the gain in the Bode plot is, the gain A can be represented as modulus of g of j omega equal to 20 log of modulus of j square omega square. First we have to take the frequency as 0.5, that is which is our lower than the first corner frequencies. We have an formula A equal to 20 log of j square omega square. In this formula we have to substitute the value of omega square. We have an omega square value is 0.5. So at last we get A equal to 12 dB. This is our first frequencies, that is lower than the first corner frequencies. And then second we have to take the frequency as 5 dB. For this we have to find the value of gain. We have already known the knowledge how to find the gain, means G equal to 20 log of modulus of j square omega square. In place of omega square just we have to replace 5 square. So at last we get A equal to 20 log of 25. So at last we get 28 dB. And after that we have to find the second corner frequencies, that is at the higher corner frequencies. For this higher corner frequency we have to use the formula. This, what is the formula means, we have already known this formula in the procedures to draw the Bode plot slide. That is gain at omega C2 in the sense second corner frequencies, that is equal to slope from omega C1 to omega C2 in the sense omega C1 is the first corner frequencies and then omega C2 is the second corner frequencies. After that it will be multiplied by log of omega C2 divided by omega C1 plus gain at omega. That is first we have to find gain at omega C1. So we have already known that omega equal to the second corner frequency. We can take this value as 50 dB. So we have to substitute this value in the above formula. So gain equal to 20 log, that is omega C1 to omega C2, that can be written as 50 divided by 5 plus 28. At last 20 log 10 we have an value of 20 and then the gain value is 28. At last the second corner frequency we get is 48 dB. And we have to find the higher frequencies. So higher frequency have to take is 100 dB. In the above case we have to take the 50 dB. So we have to use the same formula we consider in the previous case. So just we have to substitute in the gain formula we get, means gain equal to, just we have to substitute in place of 50 we have to substitute 100. At last we get 48 dB. So these are the second frequencies, that is our higher corner frequencies. So after that we have to find out the phase plot. The phase angle of the given transfer function is, we can be written as 180 degree minus tan inverse of 0.2 omega minus tan inverse of 0.02 omega. How means, in the numerator we have omega square. So generally we have j omega value is 90 degree. So we have j omega square in the numerator. So we have 180 degree. And then minus, that is in the denominator we have one pole at 0.2 omega and then another pole at 0.02 omega. That's why we can write this like this. So this is our formula to plot the phase plot in the similar graph. Next we have to find the phase angles at different values of omega, that is our different values of frequencies. So just we have to consider 7 values. So in the columns we have to take the omega, that is our frequencies, and then first pole considerations, tan inverse of 0.2 omega at one column, and then tan inverse of 0.02 column and at the third column. After that we have to find the phase angle. After that we have to take the reference points. This is our consideration only. This is not constant. So first we have to consider at 0.5. So just we have to substitute in this formula tan inverse of 0.2 into 0.5 means we get the value as 5.7 degree. After that we have to substitute this 0.5 in the above formula. So we have an value of 0.6. Then the corresponding phase angle for this frequency 0.5 is 173.7. So at omega 0.5 we have taken the alphabet as E in the similar graph. Similarly, we have to find the frequencies omega equal to 1. Just we have to substitute in this formula tan inverse of 0.1 into 1, we have 11.3 degrees. Similarly, we have to substitute this omega equal to 1 in this formula, that we will get tan inverse of 0.02 into 1. So we get 1.1 values. The corresponding phase angle for this frequency 1 is 167.6. So in the similar graph we have this, mark it as alphabet F. After that we have to take the omega frequency, that is omega value is 5. Then we have to substitute in this formula tan inverse of 0.2 into 5, that is 45. After that we have to substitute in this also tan inverse of 0.02 into omega, and the corresponding the phase angle is 129 degree. So in the similar graph it is marked as alphabet capital G. After that we have to take the omega value is 10. The corresponding phase angle is 105.3 degree. In the similar graph it can be represented as H. After that we have the omega value is 50. The corresponding phase angle is 50.7. In the similar Bode plot we have, it is marked as alphabet capital I. At last we consider as omega value is 100. That is, we have to substitute in the denominator tan inverse of 0.2 into 100. We get an value of 87.1. After that we have to substitute in the tan inverse of 0.02 omega. In the place of omega we have to substitute 100. The corresponding phase angle we get is 29.5. So this omega equal to 100 means we have to plot this in the similar graph, that is marked as alphabet capital J. So these are all about the phase angles for the different values of frequencies. After that we have to calculate the value of gain, that is gain in the sense we have to find the value of gain that can be represented as capital K. So first we can take the frequency values. 5 radian per second, that is we have already given in our question, is 20 dB. Hence at every point of the magnitude plot is obtained by shifting the plot with K equal to -1 by -28 dB, that is in our downward direction. Thus the term -28 dB is contributed by the term the gain K. So just we have to substitute in the formula, means 20 log K equal to -28 dB, in the sense means at last K value we have obtained is 0.0398. So this is our procedures to find the value of gain. After that we have to plot all these values, magnitude values and the phase angle in the similar graph. This is our similar graph representations. So this is our frequencies, that is 0.5, omega equal to 0.5, and then omega equal to 5, and then omega equal to 10, and then omega equal to 50, and then omega equal to 100 degree. The corresponding we have to take in the y-axis, in the sense means we have to start from -12 dB, that is we have already find in our third step, -12 dB, and then the next one is 28 dB, and then 48 dB. At K equal to 1 in the that is gain equal to 1 means we have an slope of plus 20 dB per decade. And then if we have if we have in the downward direction, it can be represented as -40 dB per decade. It is obtained in the slope of -12 dB. The corresponding degree is -74, and we have an K value is 0.0398, means we have an slope of plus 20 dB per decade. In the plot, the blue lines is the representation of our magnitude plot, and the black is the corresponding our phase plot in our Bode plot. In 0.5 frequencies we have an phase angle of minus 74, and then at omega equal to 5 means we have a phase angle of minus 130 degree, and in the 50 and then 100 we have an value of minus 30 degree. So these are all about the complete diagrammatic representation of our Bode plot. Next we are going to see about the just in the semi-log representations we have just we plotted the approximated value of the Bode plot. Now we have to find the exact value of the plot is, we know that the exact plot is 3 dB less than the actual plot. So thus for the actual plot the term will becomes as minus 28, that is we have obtained in our graph, plus 3 dB in the sense we get an value of minus 25 dB. So it can be contributed by the term K. So we have to equate this, means 20 log K equal to minus 25 dB means at last we get an K value is 0.0562, but our approximated value of the Bode plot we get the gain value of 0.05, but the exact plot we have an gain of 0.0562. Next we are going to see about the advantages of Bode plot. In the Bode plot it covers low frequencies as well as the high frequencies values, and then the Bode plot provides the relative stability of the terms, how means in terms of phase margin and then the gain margin. And the Bode plot, if in the previous plot, that is in the case of polar plot, Nyquist plot, just we have to plot this plot for only either open loop system or closed loop system. The only plot we can draw for both the closed loop system and the open loop system is our Bode plot. And then Bode plot improves the stability of the systems. In that Bode plot we have using the semi-log graph. So semi-log graph it converts the multiplication, that is just we have taken logarithm means the multiplications and divisions are converted into our additions. So addition and subtraction it will be easy for manual work. Here the information loss is very loss, and then in the Bode plot we consist of two plots, already we know that is magnitude and phase plot. So this magnitude and phase plots plotted separately in the sense it eliminates the confusions. At last the Bode plot is based on the asymptotic approximations that use straight line segments for plotting on the semi-log graph. So these are all the advantages of our Bode plot. Next we are going to see about the what are the limitations and then drawbacks of the Bode plots. Means here the fundamental behavior of the system that does not change frequently. How means the Bode plot is not sensitive to changes occurring in the measuring systems. That what is not sensitive to the changes means if we have any values changes in the Bode plot means the Bode plot does not react to this. That is called is not sensitive to the changes. And then after that it does not clearly predict the individual contributions of the different factors. Different factors in the sense we have three types of factors we have considered in the Bode plot. The first factor is our gain factor, and the second one is integral factor, and the third one is derivative factor. So these are the limitations of our Bode plot. So these are the references I used to make this video effectively. Thank you.